So one of the nice things about using the work energy theorem is that we just have a single equation. So at the end of the day, a single equation means one unknown if we're going to be able to solve for it. So what will happen with a work energy theorem problem is either we're going to be given the forces and the displacement, which means that we can calculate the net work because we can calculate the individual work, so the work done by the individual forces. Your unknown is going to be left on the delta K side, so the change in the kinetic energy is going to be where your unknown sits, and most often that's going to be one of the two speeds, so the initial speed your object was traveling or the final speed your object was traveling. Or the other option is you're going to be given those final and initial speeds, which means that your change in kinetic energy is a known quantity. In this case, that means the unknown has to be sitting on the net work side of the equation, and it's often going to be the magnitude of a force or some distance that your object moves through. So what we're going to do then in working these problems is pay attention to whether or not we're given the initial and final speeds. That's going to help us figure out and make sure we identify what our one unknown is. So here's an example where what we're told is we've got a 2 kilogram block. It's sliding down a frictionless ramp with a speed of 5 meters per second when you begin to push on the block with an applied force of 40 newtons. If your force is directed parallel to the ramp, how far down the ramp will the block slide before coming to a stop? Well, so when I look at this problem, what I notice is I'm given two speeds. So the initial speed the block is sliding down the ramp is 5 meters per second. And in bringing it to a stop, I'm given the final speed. It's just given to me in words, but of course I recognize that coming to a stop means the final speed is 0. So here's a situation where I know the initial speed, therefore I know the initial kinetic energy. I know the final speed, therefore I know the final kinetic energy, and in this case I don't even have to calculate its value, I just know that it's 0. And so when I think about what's going on with the work energy theorem, the delta K term is known. I know what the change in kinetic energy is, which means that the unknown has to be sitting over on the left-hand side of the equation. It's going to be somewhere in the net work term. And in fact, how far down the ramp is what I'm asked to solve for. That's basically a distance that we'll probably label D that's going to be sitting over there and factor in to how much work each of the individual forces do. Let's look at a second example. So in this case, let's say my block is 20 kilograms. It's sliding down my frictionless ramp with some initial speed when you begin to push on the block with an applied force of 140 newtons. You push on the block parallel to the ramp and the block slides 1.5 meters further down the ramp before coming to a stop. How fast was the block traveling at the instant you begin to push on it? So again, what I'm looking for here are two speeds. And again, what I notice now is I'm given one. Coming to a stop, in words, that's still a way of saying that the final speed is 0. But some initial speed means that the initial speed is my unknown. And so here, when I think about calculating out the initial kinetic energy, I don't know what this is as a value, right? I can't plug in the numbers to calculate this as a value. I do, of course, know that the final speed is 0, therefore the final kinetic energy is 0, so I know that one. But I've already identified that in terms of thinking about the work energy theorem, the unknown in my equation is sitting in the change in kinetic energy term, which means I have to be able to solve for all the individual works done on the object. So I've got to be able to solve for all the individual works that are. So I have to be able to solve for all the works done by each individual force as the object moves through this displacement. And in fact, when I think about what I'm being asked to solve for, how fast is the block traveling? Again, that's just reinforcing that what I want is a speed, and that speed's going to be on the right-hand side of the equation. All right. So what's our process here for solving problems using the work energy theorem? So just like with Newton's second law, where we had a certain process that is a general rule we wanted to work through, same sort of framework that we're going to set up for the work energy theorem. And so for starters, we're going to draw two pictures, because what the work energy theorem really cares about is the initial and final configurations of your system. We'll still draw a free body diagram, because what I want I want to use the free body diagram to be able to identify all the forces that can do work on my system. I'll calculate the initial and final kinetic energies, or at least try to identify whether or not I know what those are. I may not go ahead and calculate them out as a value. I may choose to leave it in letters as long as I can, as usual, but I at least am going to try and see, are these where my knowns are, or are these where my unknowns are? Then I'll calculate the work done by the individual forces. And again, as a general rule, I'm not going to calculate these out to a value. Instead, I'm going to figure out what these are algebraically so I can plug these into my equation. Then I'll use all that information from steps 3 and 4 to set up my work energy theorem equation. So I'll plug in all the work terms on the left. I'll plug in the two kinetic energy terms on the right. Again, what I've got is a single equation then. It should simply have a single unknown, and then I'll go and solve for that unknown. So this is the process that we'll walk through when solving problems using the work energy theorem. So as an example, let's look at the second one we were speaking of a minute ago. So again, I've got a 20 kilogram block sliding down a frictionless ramp. There's some initial speed, and I begin to push on the block with an applied force of 140 newtons. I'm going to push parallel to the ramp, and the block slides 1.5 meters further down the ramp before coming to a stop. How fast was the block traveling at the instant you began to push on it? So again, what was that initial speed the block had when it came into contact? So I'm going to draw two pictures. An initial picture, so there's the block moving initially down the ramp. I'll go ahead and draw in the applied force where I come into contact with it. And then I know that it's going to slide an additional distance down the ramp before coming to a stop. So there again is the final speed. It happens to be 0 in this case. I'm going to go ahead and identify the displacement. Go ahead and draw that onto my picture, because this displacement vector is going to be very important in calculating these individual work terms. And in this case, I'll just go ahead and recognize that that has a distance. The magnitude of the displacement has a distance of 1.5 meters that I will choose to label as d. The next thing I'm going to do is draw the free body diagram of the block. And again, the block's sliding down. It has mass, so there's a gravitational force acting on it. It's sliding down a surface, so there's a normal force. There's no friction because it's a frictionless surface. I'm pushing on the block with an applied force that's parallel to the ramp and pointing back up the ramp to slow the block down. And so the next thing I want to do is think about those kinetic energy terms. And again, here I recognize that I don't know what the initial speed is. So my unknown is sitting here in my initial kinetic energy. My final kinetic energy, of course, is 0 because my final speed is 0. And so again, just for emphasis, what this means is before I do any more work, I already recognize that my unknown is sitting on the left-hand side of the equation. That's what I'm asked to solve for, is the initial speed of the block, which means I have to be able to set up all the work terms on the left. Okay? So next what I want to do is I really want to focus on the forces in my free body diagram and how they relate to the displacement. And so we'll do this one at a time. So I'll start with the normal force. I'm going to redraw the normal force vector. There's the displacement vector. I recognize that these two forces are perpendicular to each other, which means that the work done by the normal force is 0. So any force that's perpendicular to the displacement does no work on your object. Work done by the normal 0. So come back to my free body diagram, pick a different force. So the next force I'll deal with is the gravitational force. And again, so here's the gravitational force, here's my displacement. Again, I have an equation that I can use to solve for the work done by the gravitational force. It's plus or minus mg delta h, mass positive, g positive 9.8 meters per second squared, and this delta h is a positive vertical distance that my mass travels through. And so I'm the one who's responsible for picking the right sign here, given this particular equation. And so what my vector diagram here is helping me recognize is, of course, well, the object comes down. And so if it comes down along the inclined plane, that means it has a vertical, that vertically my object is traveling downward. So I need the plus sign because gravity is going to do positive work for an object that moves down. Now I need to deal with this delta H. So I know the distance that my block travels along the incline, but of course that's not what delta H is. Instead, delta H is just that vertical distance. So what I need to do is I need to use this triangle to figure out how delta H relates to D. And so clearing everything else out of the way here, what I see is that D is the hypotenuse of this right triangle. Delta H is opposite to my 30-degree angle, which tells me that, well, the sine of theta then is going to be opposite over hypotenuse, so that's delta H over D, the way I've labeled these sides, and so I can solve that to get the delta H as D sine theta. So I can plug that into my expression for calculating the work done by gravity. So what I end up with is that the work done by gravity on my block as it slides down the incline is going to be mgd times the sine of that incline 30 degrees. So let me come back to my free body diagram again. I've got one force left. It happens to be the applied force. The applied force is constant in this case, right? It's a single value, 140 newtons. So I know that for a constant force, I can calculate the work done by a constant force by multiplying together the magnitude of the force times the magnitude of the displacement times the cosine between those two vectors. Well, I recognize that the angle between those two vectors, as I see it in my vector diagram here, is 180 degrees. So I know that I'm going to have the magnitude of the applied force, which I'll call Fa for the moment. Again, the magnitude of the displacement I've called D, and the angle between the force and displacement here is 180 degrees. Cosine of 180 degrees happens to be -1, so this negative sign that's sitting out front in my final expression simply comes from the cosine 180 term. And so I have the work done by the applied force is negative Fa times D. Well, now I can go ahead and plug all these into the work energy theorem. So again, I have the net work on the left-hand side. That's got to be equal to the change in the kinetic energy of my object on the right. I've calculated 3 work terms. I've got 2 kinetic energies. So now I can come through and plug in the work that I've already done. So I know that the work done by gravity was mgd sine theta. The work done by the normal was 0. The work done by the applied force was negative Fa times D. That's got to equal the final kinetic energy was 0, and the initial kinetic energy is 1/2 mv initial squared. And so again, looking at this expression, I know what the mass of my object is. I know what the gravitational acceleration is. I know the distance that my object travels down the incline. I know the angle of the incline, and I know the applied force that I pushed against the block with. So everything over here is a known. I know the mass over here, so sure enough, in my one equation, I'm left with one unknown. It happens to be the initial speed of the block. Algebraically, it's relatively simple to go ahead and solve, and so I get that the initial speed of the block is going to be given by the square root of 2 times Fa times D minus mgd sine theta, all that divided by the mass m. Plug in my values, I end up getting that this is 2.51 meters per second. So when the block came into contact, it was traveling at a speed of 2.51 meters per second. For those of you who are interested in working the first example, right, so you can walk through this same process. It's obviously very similar based on the way that we've set up example 1 and example 2. We've changed what the unknowns are here, so the unknown is going to be sitting on the net work side of the equation in the work energy theorem. And for those of you who choose to, you can go through and you should calculate out that the distance the block slides down in example 1 is it slides 0.828 meters down the incline.